This video will focus primarily on the third topic of the course, which is the binomial probability distribution, as well as a few other topics. In order to understand binomial random variables, we need to understand Bernoulli trials. A Bernoulli trial is a very simple concept. It's just something random that has only two possible outcomes. For example, if a basketball player shoots a free throw, they're either going to make it or they're not going to make it. If you have a newborn baby, that baby will either be male or female. Let's say you're interested in studying obesity. Well, if you randomly select a person, that person will either be obese or not. And the same thing could be said if you're randomly selecting a person and ask them if they approve of the mayor of their city or not. The binomial distribution occurs whenever you have a sequence of Bernoulli trials. On the previous slide, we were saying that whenever a basketball player shoots a single free throw, that's a Bernoulli trial, because the player either makes it or they don't. But what would happen if a basketball player shoots 10 free throws? Well, that's a sequence of Bernoulli trials. And what we're really interested in is the number of free throws that that player makes. They could make anywhere between 0 and 10 free throws. And so the total number of free throws they make is actually a random variable. Anytime we have a random variable, we want to talk about what type of probability distribution it has. And in this case, the total number of free throws made by this basketball player has a binomial distribution. So what does that mean? Well, it really just refers to the mathematical equation that we're going to use in order to calculate the probabilities for this type of problem. And we'll get into all that later. It's going to be fine. So anytime you hear the term probability distribution, and that could include binomial distribution, normal distribution, or uniform distribution, you're just talking about the equation that you use to calculate probabilities in different situations. And so again, if you have a sequence of trials where each trial has only two possible outcomes, and you have a particular outcome that you're interested in, like in this example, we're interested in when the basketball player makes the shots, and we want to count how many of those shots he makes. Anytime you're in that type of situation, you're going to have a binomial distribution. So another example would be if a couple are planning to have 3 children, and they're interested in predicting the number of girls that they'll have. So we have a sequence of Bernoulli trials. On each trial, they're either going to get a boy or a girl, and they're interested in counting the total number of girls that they get. So that's going to be a random variable. It's going to be somewhere between 0 and 3, and the equation that we're going to use to calculate the probabilities is going to be the binomial distribution. In the third example, we're going to take a random sample of 8 people from some population, and the characteristic that we're interested in is obesity. Now let's see how the binomial distribution comes into play here. We have a sequence of Bernoulli trials. Each time we randomly select someone from the population, they're either obese or they're not. And so each person here represents a Bernoulli trial. Again, what are we interested in? We're interested in counting the number of people in the sample who are obese. And that number is going to be somewhere between 0 and 8. So it's a random variable, and that random variable is going to have a binomial distribution. So we'll be able to use the binomial distribution to calculate probabilities involving this random variable. The same thing can be said for the next example. We have a sample of size 15 from a city, and we're going to ask each person in that sample whether or not they approve of the mayor. And each time we're going to get a yes or no answer. And so each one of those people is a Bernoulli trial. And that means the total number of people in the sample who approve the mayor, which is going to be somewhere between 0 and 15, is a random variable, and that random variable follows a binomial distribution. Alright, let's actually do an example where we calculate some probabilities involving a binomial distribution. We'll go back to our basketball player example where a player is shooting 10 free throws, and let's suppose that the chance of them making each shot is 40%. We're also going to be assuming that the throws are statistically independent, and I'll say a little bit more about that later, but let's skip over that for now. And the goal of this problem is to find the probability that the player makes exactly 3 shots. Okay, so how do we do this problem? The first step in this problem is actually just figuring out what type of problem it is. That's always the first step on every problem. And this is, of course, a binomial distribution problem. And we saw why on the previous slide. If you have a sequence of trials and each trial has only two possible outcomes, you're probably in a binomial distribution situation. Now, you might be wondering, aren't we always just going to be in a situation like that? Can you give me an example of a situation where there aren't just two possible outcomes? Well, what if you were interviewing a whole bunch of people and you asked each of them what their age is? Well, there wouldn't just be two possible outcomes. They might say 50, they might say 20, they might say 37. There's a whole bunch of different possible values you would get there, and so you wouldn't be able to use the binomial distribution to deal with that type of problem. Okay, so once we know we're dealing with a binomial distribution problem, the very first thing we want to do is find two numbers, n and p. These are the most important numbers that you need to know for the distribution. N is the number of trials, which in this problem is 10. And P is the probability of the outcome that you're interested in. So in this problem, we're interested in the player making the shots, and the probability of that is 40%, and so P is equal to 0.4. Now, we want to calculate the probability that this player makes exactly 3 shots. You can see in the middle there I wrote, we want to calculate the probability that capital X is equal to 3. Let's talk about what capital X is. Well, in probability theory, capital letters represent random variables, and that's the case here. Capital X represents the random variable, which is the number of shots that the player actually makes. Again, that could be anything between 0 and 10. And so capital X is a random variable. Now, sometimes the player will make exactly 3 shots, and in that case, capital X will be equal to 3. Sometimes the player will make a different number of shots, and in that case, capital X will not be equal to 3. What we want to calculate is the probability that capital X is 3. We want to calculate the proportion of the time that this player makes exactly 3 of these 10 shots. We want to figure out how likely is that to happen. Well, luckily we have this really nice formula on the next line. It says the probability that capital X is equal to little x is NCX. Now, the way that we pronounce that is we say N choose X. And I'm not going to talk about how to calculate that on this slide. I'll do that on the next slide. So let's see. This equation says probability that capital X is equal to little x is N choose X, P to the X, 1 minus P to the N minus X. One thing that we haven't discussed yet is little x. So if capital X represents the random variable, which is the number of shots that this basketball player makes, what does lowercase x stand for? Well, in probability theory, lowercase x usually stands for some specific number that you're interested in. For example, in this problem, we're interested in the number 3. And so lowercase x here is equal to 3. If you look at the right-hand side of the equation now, the only variables that appear are n, p, and x. And we know what all of those variables are equal to, so we can just plug those numbers into the equation, and that's how we get the line that's below that. The only thing we don't know is how do we calculate 10 choose 3, and we'll see that on the next slide. We're going to get 120. So using that number 120 and finishing out the calculation, you get 0.215. So that means about 22% of the time, if this basketball player shot 10 free throws, they would score exactly 3 of those. The remaining 80% of the time or so, they would get some different number. Another thing that remains is to discuss what it means for the throws to be statistically independent. That just means that the outcome on one throw doesn't have any bearing on the outcome of any other throw. For example, if this player makes the first free throw, that doesn't give them a confidence boost or anything that gives them a better chance of making the second free throw or the third free throw. Similarly, if they miss the first free throw, that doesn't mean that they're going to lose confidence and have a smaller chance of making the next shot. There's just no statistical effect either way. And this is technically necessary in order for us to do this problem, but you're not usually going to see this assumption given in a problem, but I just gave it here for completeness. Now, in the previous problem, there came a point where we needed to calculate 10 choose 3, and I didn't explain how we could get that number, so let's go ahead and do that now. To make a long story short, the best way to do it is to just use your calculator. Most calculators have a function which will just do this for you. For example, you can see at the bottom of the page I listed some instructions for doing this with a TI-83 or a TI-84. So for those, you would just type the number 10, you would click on your math button, and once you do that, at the top of the screen there are several different menus, and you want to just scroll over to the PRB, which stands for probability menu. Then you would go down to NCR and hit enter on that command. Then you would type the number 3 and hit enter again, and you'll get 120. Now, if you have a different type of calculator, I would encourage you to just try to figure out how to do it using Google. It's really easy to do that, or feel free to ask me, and I'll be happy to help you out. I can maybe post some instructions for different types of calculators in the homework and lecture help forum. You might also have a friend who's taken this course before, and they can maybe help you out with doing that. Now, some of you guys might not have a calculator that can perform these functions, so I want to go ahead, just for completeness, I want to list the mathematical explanation of how you actually calculate these numbers. And you might also be curious as to how you do that. So the first thing that we need to do is talk about factorials. So at the top there it says 4 exclamation points. So the way that we read that exclamation point is we say 4 factorial. And factorial just means start at that number and keep multiplying and decreasing until you get to 1. So 4 factorial is 4 times 3 times 2 times 1, which is 24. So the definition of n choose x is it's equal to n factorial over x factorial times n minus x factorial. And the reason it's called n choose x is because it represents the number of ways that you can take a set of n objects and choose x of them. So for example, 10 choose 3 represents the number of different ways that you can take 10 objects and randomly select 3 of them. Let's say we wanted to calculate 10 choose 3 this way. Well, then we would have 10 factorial divided by 3 factorial times 7 factorial. Well, 10 factorial is 10 times 9, so on and so forth, all the way down to 1. 3 factorial is 3 times 2 times 1. 7 factorial is 7 times 6 times, all the way down to 1. One thing that's really nice here is that all the 7s and down are all going to cancel out. And so in the top we just have 10 times 9 times 8, and the bottom we have 3 times 2 times 1, and we get 120. We can also calculate probabilities for binomial problems using a table, and this table is attached to the course webpage for this section. This is really easy. So let's say we wanted to do the problem that was on the slide 2 slides ago. Well, it was a binomial problem. N was equal to 10, P was equal to 0.4, and we wanted to calculate the probability that X was 3. If we just look up those 3 numbers, 10, 0.4, and 3 in this table, we get 0.215, which is the result that we got whenever we did the calculation by hand. So this is a really good way to calculate the probabilities, and I encourage you to do it this way. It can save you a lot of time. The only problem with this method is it won't work for every problem because there are some values that aren't in the table. Like you can see that there are no values of n greater than 10 in this table, and there are certain values of p that aren't given in the table. For example, if p was equal to 0.22, well, that's not in the table. And for any value of p greater than 0.5, it's also not in the table. It turns out that there's a way to use this table to calculate probabilities for values greater than 0.5, but I don't actually think it's worth it. It's actually kind of a pain, and I think it's actually easier to just do the calculations using the equations from before. On this slide, we're going to take a look at an example that's similar to the problem that we just did, except notice the 4th bullet. We're trying to find the probability that the player makes at most 2 free throws in this problem. This is essentially the same as the previous problem, but we have to calculate the probabilities for different values. So the first thing we have to do is think about what does it mean for the number of free throws to be at most 2? Well, the number of free throws made can be any number between 0 and 10. So if it's at most 2, that means it has to either be 0, 1, or 2. And so if we want to find that probability, we just have to add those probabilities together. Probability x is 0 plus probability x is 1 plus probability x is 2. Now, each one of those numbers can be calculated using the equation that we used. The only thing that changes in each case is the value of x. So in the first one, x is 0, and you can see there's a bunch of zeros everywhere. For the second one, x is 1, and you can see where the x's have been replaced by 1s, and so on and so forth. So you can calculate each one of those numbers and then add them together. You get 0.1672. You can also just use the table on this problem to calculate all the probabilities. You can see that the numbers that we calculated with the equation are just equal to the numbers that are in the table. So this can save you a ton of time. Alright, let's take a look at a new binomial example. Let's assume that we're taking a random sample of 8 people from a city, and 30% of the people in that city are obese. We want to find the probability that more than 5 people in the sample will be obese. As discussed before, we know this is a binomial problem because we have a sequence of 8 trials, and we know that on each trial there are only 2 possible outcomes. And we know the most important thing to do in a binomial problem is to figure out what n and p are. Well, n is the number of trials, which is 8, and p is the probability that a randomly selected person will be obese, which is 0.3. If we're trying to find the probability that more than 5 people are obese, that includes the possibilities of 6, 7, and 8, because you can't go above 8 if your sample size is 8. As you can see, we're just using the equation to calculate those probabilities, and the result we get is 0.0113. This is also another example where we can completely avoid doing these calculations by just relying on the table. It's worth mentioning that that third probability that we calculated was 0.0000656. Now, if you calculate this with your calculator, it'll say 6.56 times 10 to the negative fifth. Just as a reminder, that just refers to scientific notation. So that just means take the decimal point, move it 5 places to the left, and that's how we got the number that we arrived at here. Now, if you look at the table, it doesn't say that. It says 0.0001. The reason for that is all of the numbers in the table are rounded off to the 4th decimal place. If you take 0.00006 and you round it to the 4th decimal place, you get 0.0001. So that's how they came up with that. Now we're ready to work some problems where we find the mean, variance, and standard deviation for a binomial distribution. And we're going to be using the 2 formulas on this slide. The mean is represented by the Greek letter mu, and the formula that we have here says that mu is equal to np. The variance for the binomial distribution is represented by sigma squared, and that says sigma squared is equal to np times 1 minus p. Alright, so we're going to return to our basketball example where a player is shooting 10 free throws, and they have a 40% chance of making each one. The first question asked in this problem is, find the number of shots that this player will make on average. Now, the average is the same thing as the mean. So we're just going to take mu equals np, and we recall that n is 10 and p is 0.4, so 10 times 0.4 is 4. This makes perfect sense. If this player makes 40% of his shots on average, and he shoots 10 free throws, well, then on average he's going to make about 40% of those 10 free throws, and 40% of 10 is 4. This doesn't mean that every single time this player shoots 10 free throws, he will make 4 of the shots. Again, it's random. Sometimes he won't make any of the shots. Sometimes he could make 10 shots. Any number between 0 and 10 is a possibility. So what does this mean? Let's say that this player shoots 10 free throws and writes down the number of shots that he makes. And he does this every day. And so one day he shoots 10 free throws and he makes 3 of them, so he writes a 3 down. Next day he shoots 10 free throws, he makes 7 of them, he writes a 7 down. And he just keeps writing these numbers down for a very long period of time. then if you took the average of those numbers, you would get something extremely close to 4. And the longer you let this go on, the closer that average will get to 4. The second question asked in this problem is to find the variance and standard deviation of the number of shots made. As before, once we get the variance, we can easily find the standard deviation by just taking the square root. So let's just focus on finding the variance. The formula for that is sigma squared equals np times 1 minus p, which is 10 times 0.4 times 0.6, which is 2.4. So the variance of the number of shots made is 2.4. Once we find the variance, we want to find the standard deviation, which is the square root of 2.4, and that's 1.55. But what does the standard deviation tell us? Let's go back to the fact that the mean in this example is 4. That means that if this basketball player shoots 10 free throws, on average, he'll make about 4 of those shots. Now he's going to make a whole bunch of different numbers each time he does it. Sometimes he'll make only 0 shots. Sometimes he'll make 3 shots or 5 shots or 7 shots. Sometimes he'll be below 4. Sometimes he'll be above 4. But in the long run, those numbers are going to average out to 4. The standard deviation tells us about how far away from 4 he will typically be. So since the standard deviation is 1.55, that means he'll make about 4 shots on average, plus or minus about 1.5 shots. Also, if you look back to chapter 2, we talked about the normal rule, which said that about 95% of the time, an observation will be within 2 standard deviations of the mean. And now that only works for normal distributions, but it turns out that this distribution is approximately normal. So if we take the standard deviation, which is 1.55, and multiply it by 2, we get 3. And if we take 4 minus 3, we get 1. If we take 4 plus 3, we get 7. If you calculate the probability that this basketball player makes between 1 and 7 shots, the answer is about 98%. So, in other words, the basketball player could make anywhere between 0 and 10 shots, but he's actually very unlikely to have a number that's more than 2 standard deviations away from the mean. He has a 98% chance of being between 1 and 7. So that kind of explains why we're interested in calculating the standard deviation. Alright, we're finally done discussing the binomial distribution, and now we're just going to move on to some of the miscellaneous topics that are covered in this chapter, and they're on your homework. The first thing we're going to talk about is the difference between discrete random variables and continuous random variables. So let's talk about discrete random variables first. I want to try to explain which types of random variables are discrete. So first of all, if the number of possible values for a random variable is finite, then that random variable is automatically discrete. And finite just means limited. There's a fixed limited number of possible values for that random variable. So for example, if you randomly select someone and the variable that you're interested in is gender, then there's 2 possible values, male and female. That's a finite amount. It's a limited amount. So gender would be a discrete random variable. Another example would be smoking status. Someone's either a smoker or they're not a smoker. So there's only 2 possible values. That's a finite number. That's a discrete random variable. Or maybe you want to look at someone's state where they were born or where they live. Well, there's 50 possibilities of Alaska through Wyoming there. So 50 is a pretty big number as far as number of possible values goes, but it's still finite. It's not infinite, so that would be a discrete random variable. You can also have discrete random variables that are actually equal to numbers. So like if you take a sample of size 5, so you randomly select 5 people in New York, say, and you count the number of people in that sample who have skin cancer. Well, that's going to be a number between 0 and 5. And so the possible values of that random variable are 0 to 5. So number of people in the sample with skin cancer is a discrete random variable. So we just saw that if the number of possible values for a random variable is finite, then it's automatically discrete. Well, actually some random variables that have infinitely many possible values are also discrete. Here's how you know. If a random variable has infinitely many possible values, and there are discrete gaps between the numbers, in other words, there are big spaces between the numbers, then it's actually still a discrete random variable. So an example of this might be if you wanted to look at the number of leukemia cases occurring in New York in 2012. Well, the possible values for that random variable are 0, 1, 2, 3, and so on and so forth. So there's an infinite number of possible values because there's no clear upper bound on how many leukemia cases you could have. But between any two of those numbers, there's a definite gap. So for example, between 1 and 2, there's a gap of size 1 there. And those numbers are not in the set. So in a situation like that, you're dealing with a discrete random variable. A good rule of thumb is if you're dealing with whole numbers only, then that's a discrete random variable. Whereas if decimal numbers and fractions are allowed, then you're probably dealing with a continuous random variable, which we'll see on the next slide. Just to finish this slide up, it gives another example. Number of phone calls received by a company in 1 hour. Again, there's no clear upper bound on that. It could be 0, 1, 2, 3, and it could be an arbitrarily large number. But the point is, there are definite discrete gaps between those numbers. Decimal numbers are not allowed, and so it still counts as a discrete random variable. Alright, so what are continuous random variables? If a random variable has infinitely many possible values, and those values form a continuous interval, then the variable is continuous. So let's figure out what that means. A good example of a continuous random variable is height. So if you take a randomly selected person and measure their height, then you could potentially get almost any positive number. I mean, there's definitely an upper bound, but we don't really know what that is. Let's just say that you're confident that the height of the person will be between 60 and 80 inches, just for the sake of argument. The thing is, there are still infinitely many possible values because you're not restricted to whole numbers. Someone's height doesn't have to be a whole number of inches, like 60 inches, 61 inches, 62 inches. It could be 62.58743 inches. It could be any decimal number in there. And so you've got this spectrum of possible numbers. You've got a continuum of possibilities. There are infinitely many possible numbers between 60 and 80 because we're allowing decimal numbers to be included. Another way to think about it is between any two numbers, there are not discrete gaps in this situation. Like if you look at the number 60 and the number 61, there's no gap in between those because all of those decimal numbers in between are also possible values, and so the numbers are all mashed in together in this continuum. So again, a good rule of thumb is if you're dealing with a categorical variable like gender, ethnicity, county of residence, something to that effect, it's definitely a discrete random variable. Now if you're dealing with a numerical value that uses whole numbers, it's going to be a discrete random variable. If it's using decimal numbers, it's going to be a continuous random variable. So some other examples of continuous random variables include things like weight, income level, cholesterol level, and blood sugar level. This is a nice and simple slide that involves the concept of probability mass functions. In this example, let's assume that the probability that a person visits the doctor a certain number of times is given by the table on the slide. So they can visit the doctor somewhere between 0 and 4 times, and for each of these values the corresponding probability is given. So they have a 30% chance of visiting no times, a 50% chance of visiting once, etc. Well, the random variable number of doctor's visits is a discrete random variable. There's only finitely many possible values. Anytime you have a discrete random variable, you can make a table like this. Except for the case where you have infinitely many possible values, and then you can just write an equation that describes this. So you can either make a table like this, or you can construct an equation that takes care of this function. And this table or equation is referred to as a probability mass function, or PMF for short. probability mass functions are really just another way of describing a probability distribution, which we've already discussed for the binomial example. But this problem's really easy. Let's just go ahead and take a look at this problem. It says find the probability that this patient Victor visits the doctor once or twice. Well, we would just take probability of one visit plus probability of two visits. Add those together, we get 0.6. 2 times or less. Well, 2 times or less would include 0, 1, and 2. So we would do 0.3 plus 0.5 plus 0.1 and get 0.9. 3 times or more. Well, that would include 3 and 4, which is 0.08 plus 0.2, and that gives us 0.1. And the probability that this person visits the doctor exactly once would be 0.5. This is another pretty simple slide that talks about what happens if you have a collection of things of 2 different types and you want to randomly select one of those and you're interested in calculating a probability. Let's say we have a group of people that consists of 10 males and 14 females. What's the probability that a randomly selected person from this group is female? Well, we have 24 total people, and we're just randomly selecting them, so they're all equally likely to be selected. So if we have 24 total people and 14 of them are female, the probability that we randomly select a female is going to be 14 out of 24, which is 0.583. Another example of this would be if you have an urn that contains 5 red balls and 3 green balls, and you randomly select a ball. Well, what's the probability you get a red ball? Again, you've got 8 total balls here, and you're just as likely to select one as any other one. So since there are 5 red balls and 8 total balls, the chance is going to be 5 over 8, which is 0.625. Alright, well this is the last slide for this presentation, and it discusses analyzing new tests for detecting diseases. The disease under consideration might be skin cancer or something like that. Now, for cancer, we have the method of detection of biopsies. We can take a small amount of tissue and send that to a lab. The lab analyzes it and returns a test result. The advantage of this method is that it's accurate. If the test says that someone has the disease, they're quite likely to have it, and if it says they're negative, they're very likely to not have it. So it sort of forms a gold standard of tests. The problem with the biopsy method is that it could be expensive or time consuming. So it would be nice if you could develop a new test which is faster and cheaper. So in particular, if the patient could get a test result the day that they come into the doctor's office, that would be great. Well, the problem with that though is the new test is not as thorough as the gold standard, and so it probably won't be as accurate, and therefore it becomes important to assess how accurate it is. You know, maybe it's reasonably accurate, and in that case you can at least put some trust in it while you're waiting for a biopsy. On the other hand, if the new test is extremely inaccurate, there's really no point in even using it. You might as well just wait for the biopsy. The table on this slide presents an example of a hypothetical test that involves 200 people. 100 of the people tested positive according to the gold standard, which basically means that they have the disease. We're just going to assume that the gold standard is 100% accurate in this example. And 100 people also tested negative, and so they don't have the disease. So there's 200 total people in this study. Now, each person in this study was also tested for the disease using the new test. For example, of the 100 people who have the disease, 70 tested positive under the new test and 30 tested negative under the new test. So the percentage of people who have the disease and who actually tested positive using the new test is 70%. And that's referred to as the sensitivity. So you can see that we have these 5 metrics underneath the table that are kind of measuring different aspects of the accuracy of the new test. So the sensitivity is defined as the percentage of true positives who test positive using the new test. In other words, the percentage of people who really have the disease who actually test positive for the disease. Obviously, we would like this to be as close to 100% as possible. In this example, it's equal to 70%. Specificity is the percentage of true negatives who test negative. In other words, the percentage of people who really don't have the disease who actually test negative. In this example, there are 100 people who do not have the disease. 95 of those people test negative. So the specificity is 95 out of 100, which is 95%. The next quantity that we're going to look at is the PVP, which stands for predictive value positive. It's the percentage of positive tests where the person truly is positive for the disease. In other words, if you look at everyone who tested positive under the new test, what percentage of those tested positive under the gold standard? So there are 75 total people who tested positive using the new test, and 70 of those really do have the disease because they tested positive under the gold standard. So 70 out of 75 is 93%. That's how you calculate that number. The false positive rate is exactly what it sounds like. It's the chance that someone will get a false positive if they don't have the disease. This is pretty straightforward. There are 100 people in this example who did not have the disease, but 5 of those people tested positive anyway. Those are false positives. So 5 out of 100 is 5%, and the false positive rate is 5%. Similarly, the false negative rate is the probability that someone who is positive for the disease will actually test negative for it. And so there are 100 people who are actually positive for the disease. 30 of those tested negative, and so the false negative rate is 30 out of 100, which is 30%. All right, well, that concludes this supplemental lecture. And let me know what you guys think of this. If you have any suggestions for improvement, or if there are things that you particularly liked or didn't like, just let me know. But thank you for listening to this, and as always, let me know if you guys have any questions, and I'll be happy to help you out. But I'll see you next time.